Hello everyone and welcome to this session. My name is Valentin Toby. I'm a strategic security architect, and in this session I will demo how the new F5 distributed cloud web application firewall protects a web application against a modern day attack such as Node4Shell. We selected Node4Shell for the purpose of this demo, as this attack has made a lot of headlines lately due to its severity and attack surface. First, let's see what is a Node4Shell attack. The underlying issue here is that we have a vulnerable logging utility, Apache's widely used Log4j, that in some versions executes code downloaded from third-party LDAP servers without proper checks. To exploit this vulnerability, the attacker needs to control a rogue LDAP server and then submit a request to the vulnerable server directing Log4j logging utility to download and execute code from that rogue LDAP server. Once the downloaded code gets executed, the attacker gets near total control of the vulnerable server, and in some of the most dangerous exploits, such as Log4Shell, the code instructs the server to open a reverse shell session and attach itself to a socket on the attacker's machine, effectively granting the attacker remote shell capability. I will quickly demonstrate such an attack against an unprotected, vulnerable application. I already configured the vulnerable application and the compromised LDAP server to run in F5 distributed cloud. You can see here the load balancer that exposes my vulnerable server to the internet. To perform the attack, I first need to open a socket waiting for the reverse shell connection, and for that I will be using the netcat utility. I will then open another shell and execute the attack, in this case a simple web request with a header that would normally be logged via Log4j, but in this particular case there's a twist. I'm asking Log4j to download and execute code from my rogue LDAP server. And there it is. The reverse shell session is connected, and I can check that I gained access to the vulnerable system. Now, to understand how we can stop this attack, we need to take a quick look at its taxonomy. This vulnerability is an instance related to two generic types of weaknesses: deserialization of untrusted data and improper input validation. Mapping these two weaknesses to the OWASP Top 10 web application security risks, you will notice that deserialization of untrusted data maps to software and data integrity failures, while improper input validation maps to injection risks. You will also notice that in the latest 2021 version of OWASP Top 10, the injection attack risk category has been downgraded to the third position, compared to the top place it held in the 2017 ranking. But the Log4Shell attack proves how dangerous these vulnerabilities still are. Besides these two initial risk categories, once the CVE is disclosed, Log4Shell makes its way into the vulnerable and outdated components risk category. For a brief overview of OWASP Top 10, I will leverage the extensive research done by Byron McNaught, Senior Solutions Marketing Manager. Briefly, the OWASP Top 10 represents a broad consensus about the most critical risks to web applications, not necessarily the top 10 impacts, likelihoods, or vulnerabilities. While we don't have time to get into a complete breakdown of the OWASP Top 10 2021 right now, we hope you register for our webinar in March, when we will do just that. It is important to note that the OWASP Top 10 goes well beyond basic or checkbox level security. The Top 10 now encompasses modern application architectures that leverage cloud, containers, APIs, mobile apps, and complex software supply chains and CI/CD pipelines. OWASP also emphasizes a data-driven methodology in its 2021 update to capture more weaknesses and potentially more vulnerabilities, as well as given more credence to security practitioner opinions through its community survey. For 20 years, the top risks remain largely unchanged, but 2021 brings a new wave of risks in application security, specifically the need for security end-to-end, from architecture to design to code to operations. While the OWASP Top 10 is a flagship project for guidance on securing web applications, and OWASP has API Top 10 and Automated Threats Labs projects, there is considerable overlap between these projects, and it is increasingly clear that integrated solutions that mitigate vulnerabilities and abuse for web apps and APIs are in order. F5 Distributed Cloud Web App and API Protection provides effective and easy-to-operate security in a cloud-delivered as-a-service platform and integrates web application firewall, API security, bot defense, and DDoS protection to help you put OWASP guidance into practice without the operational complexity of managing several disparate solutions. One of the unique capabilities of F5 Distributed Cloud is its ability to provide consistent policy enforcement across clouds and architectures, which of course will help considerably against security misconfiguration. It is also API-driven in its deployment and operation, providing easy integration into CI/CD pipelines and broader security ecosystems such as event management systems. Now that we've studied this attack's taxonomy, let's see how we can actually stop it with the help of our distributed cloud WAF. The classic way to recognize injection attacks is to check the incoming request against a database of signatures belonging to known threats. To reduce the chance of false positives and understand the specific details of each attack, F5 WAF technology leverages the threat campaigns functionality. The F5 Distributed Cloud WAF shares the same engine with the industry-leading BigIP Advanced WAF and Nginx Protect WAF, enabling the highest level of protection available on the market. As such, it is actually protecting against the Log4Shell attack out of the box with no additional configuration needed. Let me demonstrate how to quickly protect the vulnerable application with our distributed cloud WAF. First, I will configure the distributed cloud WAF with default settings. The second step is to attach it to the load balancer that exposes our vulnerable application. The configuration is done. Let's rerun the attack. I'll open the socket again and send the same request as before. You will notice the request was blocked and no incoming reverse shell connection was received. Let's look at the security events log under the load balancer's security monitoring dashboard. Now let's examine the blocked request and see the details. You will see this request matched a couple of generic signatures, so we identified the attack classes it belongs to. But more importantly, you may notice that the threat campaign feature of Distributed Cloud WAF identified the exact instance of this type of attack. As shown in the configuration section of our demo, this powerful feature is enabled by default. It relies on a data feed generated by our security researchers, ensuring not only very quick vulnerability patching, but precise identification of real attacks observed in the wild, and this gives you extra confidence in the actions taken by the distributed cloud WAF and more context in your analysis. This concludes our demo. I hope you found it interesting. Thank you for your attention.